Good morning, students. Say in the last Zoom meeting, we have seen that the packing of the particles or spheres in one-dimensional, two-dimensional, and three-dimensional structures. Okay. That also I have just uploaded the video of that after taking the Zoom meeting. So that packing efficiency. This packing efficiency also we have seen in the last Zoom meeting. The whole things, how the packing efficiency of the simple cubic lattice and body-centered cubic lattice, and the number of particles and unit cell per given in a given weight or mass of a substance. That everything we have seen in Zoom meeting. So this is the revised video, or it is just revision for you. I am just going to upload again. Now packing efficiency. Packing efficiency and packing fraction. Packing fraction means that is the volume occupied by the number of particles divided by the volume of a unit cell, total volume of a unit cell. This is the packing fraction. And to this packing fraction, if you multiply by 100, that becomes the packing efficiency. That is, packing efficiency is equals to, I will just write the formula of packing efficiency. See here, packing efficiency is equals to the volume occupied by the spheres or atom divided by total volume of unit cell into 100. So this is the packing efficiency we can calculate by this formula. Now say first of all, let us say packing efficiency of the simple cubic lattice. The packing efficiency in simple cubic lattice. Packing efficiency in simple cubic lattice. Okay, see here, let us see the diagram. Actually, how to draw the diagram, that I will tell you. See here, simple cube is, we just draw the simple cube like this way, is it? This is the simple cube we can draw in a simple method. Now in this actually simple cubic cell, 8 atoms are present at the 8 corners, and to each cell 1/8 part gets to each cell, because at each corner of a unit cell is shared with the other 8 cubic cells. That's why each atom is divided to 1/8 part to each individual cell. That's why 1/8 into 8 corners is equals to 1 particle. That means 1 particle is present in the that simple cubic cell. Okay, I will just draw the diagram in the for the calculation. See, this is the simple cubic unit cell. Edge length, all the edges are equal in length. Edge length of this cube is equals to A. Okay, now see here, the atoms are like this way. See here, in this way the atoms. Okay, I will just draw the full circle here. Okay, now this to this point is the R, this to this point is also R. बरोबर. So here we can just A is equals to twice of R. इथे काय असेल, A is equals to 2R, because A is the edge length from this to this point, or this to this point, this to this point. All edges are equal in length, but this is this distance to this distance, it is a twice of radius, is it? That's why A is equals to 2R. That we are going to see later on. Now packing efficiency in simple cubic lattice, we go through the steps. Stepwise we can do the calculations. Number 1, see here, number 1, that is radius of sphere. Number one step is radius of sphere. That means the relation between radius and edge length, that we are going to see. हे आपल्याला बघायचं आहे, रिलेशन फाइंड आउट करायचं आहे रेडियस आणि ए मधलं. ओके, नाउ फॉर दिस ॲज यू नो that is right now we have just seen A is equals to twice of R, therefore R is equals to A by 2. This is the relation between radius and edge length A. Okay, the next is volume of the sphere. Now let us see the volume of the sphere. Second step, volume of sphere. Okay, volume of sphere, we know the formula of volume of sphere, that is equals to 4 by 3 pi r cube. This is the formula for volume. Now the value of r that we can substitute as a by 2 here. The equation will become 4 by 3 pi into a by 2 the whole cube. Let us solve this. 4 by 3 into pi into a cube divided by 8. This is 4 2s as 8. So finally we can write here pi into a cube divided by 6, pi into a cube divided by 3 2s are 6. Okay, this is the volume of one sphere. Now 3, total volume occupied by all spheres since simple cubic cell consists one sphere or one atom, right? Therefore the total volume occupied by all spheres is equals to 1 into pi into a cube divided by 6, that is equals to pi into a cube divided by 6. Oh, see here, I will just push it up. Okay, now see here, the second step. First step was to decide the relation between R and A. Now second, volume of sphere, volume of one sphere or one atom is equals to 4 by 3 pi r cube. Therefore 4 by 3 pi into r, the value of r is a by 2, that is a by 2 its cube. 4 by 3 into pi into cube of this a cube divided by 8, this is 4 2s as 8. Now finally pi into a cube divided by 3 to the 6. Okay, so this is the volume of one sphere. As you know, the total volume occupied by all spheres means the spheres present in the simple cubic unit cell. Now simple cubic unit cell consists one atom only, that's why 1 into this is equals to pi into a cube divided by 6. So this is the volume occupied by only one sphere which is present in the simple cubic unit cell is given. Now finally we can just find out the packing efficiency. Now fourth point as packing efficiency. Okay, packing efficiency is equals to, as the formula, what the formula, that is volume occupied by the sphere pi into a cube divided by 6. Okay, this is the volume occupied by the sphere or spheres divided by volume of cube. What is volume of cube? That is a cube. As the edge length of the cube is a, that's why its volume is a cube into 100. Okay, now see this a cube gets cancelled with this a cube, so what is left? That is pi upon 6 into 100. Okay, so I can write that is equals to 3.142. this is the value of pi divided by 6 into 100. Okay, after calculation of this multiplication and division, you will get 52.36, the answer final, that is 52.36%. So this is the packing efficiency, means out of the 100% volume of the unit cell, 52%, only 52% of 52.36 is occupied by the particles or atoms or spheres. So remaining, is it remaining? So remaining is the void space. Okay, that is remaining volume, that is 47.64% is the empty space, or it is void space, is it? So this is the packing efficiency of that is simple cubic lattice and simple cubic unit cell. Okay, now let us say the packing efficiency in body centered cubic lattice. Okay, now body centered cubic lattice. In body centered cubic lattice, one atom is present at the center of the body of the cell along with the 8 corners at the center of the cell, along with the 8 corners, is it? So like this, but actually that is, it may be like this. So this is the front view, suppose. So this is the front view. At the center of the cell there is a one atom. That means total number of atoms present in the body centered cubic lattice or body centered cubic cell is 2 atom. That means one atom at from the 8 corners and 1 atom at the center. So 2 atoms are present. Now let's just draw the diagram like this way. So this is the cube. Now see, now consider the one atom at this corner, back corner. Okay, one atom at the back corner, and that is one atom at the center of the cell, and one atom from this. I will just redraw it. One atom at this corner, back corner, and one atom front corner, in this way, and one atom at the center of the body. Okay, so let us join this, and this we can join. Okay, see here, suppose this is the point F and this is point E. This point is supposed to D and this point is supposed A at this point. Okay, now see, from here edge length, as usual, edge length is equals to A. Okay, now from triangle FDE or FED, D is the right angle. See here, in triangle, first of all what we are going to find out, that is radius of sphere or atom, that is the relation between R and A. So consider the in triangle FED or FDE, angle D is of 90 degrees. Okay, Now therefore in right angle triangle FED, FE square hypotenuse square is equals to FD square plus DE square. That means what is A? This is A and this is also A. So that is equals to A square plus A square. So FE square is equals to twice of A square. Okay, this is suppose 1. Now consider the triangle FAE or FEA. Okay, now I will write now in triangle FEA, angle E is equals to 90 degrees. Okay, therefore we can write as FA as a hypotenuse. AF or FA is a hypotenuse, that is equals to FE square plus EA square. FE square we know from the one. FE square is equals to twice of A square. Is it? Plus EA. EA is again edge length, that is A square. Is it? That is equals to thrice of A square. That is AE square is equals to thrice of AE square. Now taking square root on both sides. See here. 2A square plus A square, thrice of A square. Taking square root on both sides, AE is equals to root 3A. Okay. Now see. Okay. Now let us say FAE. See here, I will show you the diagram. For the diagram, AE, see this is AE, seems to appear as the distance which is 4 times of radius. This to this 1 radius, this to this diameter means 2r, and this to this distance, center to this circumference of this circle is r. Center to circumference of this circle is r, and this is twice of r because it is the diameter of middle circle. So this is FE, AF or FA. AF or FA is equals to 4 times of r. So for this we can write here, okay, we can basically write here, no doubt, AE, since AE is equals to 4 times of r, therefore 4 times of r is equals to root 3 upon A. 4r is equals to root 3 upon root 3 into A. Therefore we can write the relation between r and A now. R is equals to root 3 upon 4 into A. So this is the relation between r and A. Okay. Now as see here. So this is the radius of sphere. That is the radius of sphere we have found. Now after this, the volume of sphere, let us see the volume of spheres. Okay, now see here, second point, volume of sphere. Volume of sphere formula is 4 by 3 pi r cube. 4 by 3 pi r cube. The value of r is here, is it? So we can substitute 4 by 3 into pi into r cube is root 3 upon 4 into A, the whole cube. That is equals to 4 by 3 pi into root 3 cube, means root 3 into root 3 into root 3, that is 3 root 3 upon 4. That's sorry, it here cube of 4 is 64 A cube. Okay, now 16 4 is 64, and this 3 this gets cancelled, is it? Now therefore what is left here, that is root pi into root 3 into A cube divided by 16. Pi into root 3 into A cube divided by 16. Okay, I will write here. See, volume of sphere is equals to pi into root 3 into a cube divided by 16. Now third one, total volume occupied by two spheres as it is BCC. Okay, because two atoms are present in body centered cubic cell, right? So we can write that is equals to 2 into this, that is pi into root 3 a cube divided by 16, that is 2 8s as 16 is equals to pi into root 3 a cube divided by 8, a cube divided by 8. Okay, now packing efficiency, we can just apply the formula. Packing efficiency for this type of lattice or cell is equals to volume occupied by the unit cell pi into root 3 divided by 8 into a cube, the whole divided by the volume of unit cell is a cube into 100. So we can just cancel this. Okay, what is remaining? Pi into root 3 upon 8 into 100. So after multiplication of this, that is the value by taking the value of pi, that is 3.142 and the value of root 3 into 100 divided by 8, we can get 68% of the volume is occupied by the spheres or atoms in body centered cubic cell, and this is occupied volume. Is it? It is say found that in BCC the efficiency is more than in the simple cubic unit cell. That means how many void spaces remained here? 32% of the space of the total space is empty, or it is void space. Okay, so this is the packing efficiency of the body centered cubic lattice. Okay, now let us see the number of particles first in x gram or given mass of a metallic crystals. Number of particles and unit cells. If given mass, if a mass is given and that means so and so grams, then find out the number of particles from the given mass of the metallic crystals. Now how to find out that? We know that density of the crystal lattice or unit cell is given like this way, that is rho is equals to n into m upon a cube into Ne, where n the number of atoms or particles per unit cell, capital M is the molecular mass, a cube is the volume of unit cell as a is the edge length of the unit cell, and Na, this Na is Avogadro's number. The value is 6.022 into 10 to the power of minus 20, that is 23 number of particles present per mole of a substance. Okay, now from this we can rearrange, that is to get M is equals to rho into a cube into Na upon n. Now as we can rewrite or represent here, molar mass contains molar mass M, molar mass M contains Na, means this much number of particles, because this much particles are per mole, Na number of particles, then X given mass of a metal crystal contains how many particles? So particles, this into this, X into Na upon M, is it? So M, we know M is equals to this, so after substituting here we can write X into Na, and this denominator gets to numerator and rest in denominator, rho into a cube into Na. This Na gets cancelled, and what is left? X into n upon rho into a cube. So this much particles are present in x gram of the given crystal. So given crystal X gram contains X into n upon rho into a cube number of particles. So this is the way how to find out the number of particles from the given. So given weight is here, this. If given weight X is multiplied by n upon rho into a cube, you will get the number of particles in that present in that crystal. Okay. Let us see to find out the number of unit cell in a same given X gram of the crystal. So the next thing is to find out the number of unit cell in X gram of the metallic crystal, or the number of unit cell present in or constitute in X gram of the metallic crystals. Now we have find out number of particles in X gram of the crystal, X into n upon rho into a cube. This we have calculated. We have just seen how to find out the number of particles. So this is the formula like, okay. Now to find out the number of unit cells in X gram of the crystals, so the n number of particles constitute 2 or corresponds to 1 unit cell. That is the construction. Now therefore this much number of particles corresponds to how many number of unit cells? Is it n number of, as the n number of particles are present in 1 unit cell that we have just considered. So n number of particles corresponds to 1 unit cell. So this much number of particles corresponds to how many unit cells? That is equals to this into 1 divided by this n. So x into n upon rho into a cube into 1 divided by n. That is equals to this n, this n gets cancelled, and that is a upon rho into that is a cube, where x the given mass of the crystal, metallic crystal, and rho is the density, a is the edge length, its cube, a cube. Okay. Now in terms of volume, how to find out the number of unit cells? If volume of crystal is equals to V units, suppose V units, we know that volume of unit cell is equals to a cube. Therefore number of, see here, the volume in, that is the number of unit cells from the volume of the crystal. If the volume of the crystal is equals to V units, then the volume of and the volume of unit cell, that is we know that is a cube. Therefore number of unit cells in volume V is equals to V upon a cube number of unit cell. This is the formula in terms of unit cell. Okay.